Yeah, this is the outline of my presentation. First is what is quantum computing, because the part is the introduction, then principle of quantum mechanics, then qubits, quantum computing use cases, quantum advantage versus quantum utilities, quantum computing components, quantum software, quantum computing applications, quantum computing in India, and computing, the labs are there. There are different labs developed by the different industries that will see some labs. First, we'll see this definition of quantum computing, because quantum computing, maybe you heard the word from many years or recently. We try to see that how this quantum computing is different from classical computing as our normal computing. Normal computing we are using daily, and these computers or machines used for daily work. But how the quantum computing is different from the normal or which we are using the regular computing of machines. We can see the definition here. Computing, this is an emerging field of cutting edge computer science. We can see this is there are the unique qualities of quantum mechanics to solve the problems beyond the ability of even the most powerful classical computers. We'll see that what type of what type of problems are here. The most problems which are very difficult to solve, which requires the more time, that problems can be solved in the quantum computing. This is a brief, we can say the definition of quantum computing. It's looking like this. We'll see that how this quantum computing or this machine is looking in the lab. The field of quantum computing contains a range of disciplines, including there is a quantum hardware and quantum algorithms. This is not a normal computer. There should be hardware. There should be the algorithms. As you heard that supercomputers are there. Supercomputers can be solved some problems, or it takes some time. Here in the communication field or in the any machine field, we'll see that time is very important. The difficult problems or complex problems can be solved in the quantum computing as a fast, which is not possible in even supercomputing or daily users computing. We'll see that quantum computings are the computers that consist of quantum bits. Normal computers, all of you know that, but here it consists of the quantum bits or qubits. It's short form, we can say it is a qubits that play a similar role in the bits. We can see the today's digital computers. All of you know that in the digital computers will be see there is a 0 and 1. But in the quantum computings, we'll see that it should be stored in the quantum bits. Is it audible?
Yes.
Okay, thank you. We can see here quantum computers consist of quantum bits, like normal computers or regular computers having the digital computers in the form of 0 and 1. There are the 4 principles of quantum mechanics. For understanding the quantum computing, there should be required 4 key principles of quantum mechanics. There are the 4 principles. First is the superposition, second is the entanglement, third is the decoherence, and fourth is the interference. What is this superposition? In the superposition, we can see here, this is a state in which quantum particles or systems can represent not just one possibility, but a combination of multiple possibilities. We'll see that there are multiple things comes together and make a machine powerful. Entanglement in that is the process in which multiple quantum particles become correlated more strongly than regular probability allows. Here we'll see that this should be the more correlated to each others. In that figure or in that we'll see that how they are correlated to quantums can be correlated to each other. Next concept or next principle is the decoherence. This is the process in which quantum particles and systems can decay collapse or change. There is a possibility of modify, there should be possibility of convert into single states into measurable classical physics. Then interference, this is a fourth mechanism, or we can say the principle in the quantum mechanics. In this mechanism, interference is the phenomena in which entangled quantum states can interact and produce more and less likely probabilities. Then we'll see the qubits. As I said, qubits in the normal computers, the data is stored in the form of 0 and 1 in the digital formats. In qubits, we'll see that while the classical computers rely on the binary bits zeros and ones to store and process the data, but in the quantum computing, what we can see, the quantum bits or qubits in the superpositions. Here qubits can behave like a bit or store either 0 or 1, but this should be weighted combination of 0 and 1 at the same time. When we are going to combine these superpositions, can scale the exponentially, that it can be increased fast, because we are going to solve the difficult problem or complex problems, then it is possible through the qubits because it's increase or scale up exponentially. For example, 2 qubits are there, they can compute with 4 pieces of information, then 3 can compute 8, 4 can compute with 16, and so on. This way it can be scaled exponentially and increase to solve the difficult problem. Here we can see qubits can be created, manipulated, or measure quantum particles. For example, such as photons, electrons. This is from the physics, trapped ions, and atoms. For manipulating such particles, qubits must be kept extremely cold to minimize noise and prevent them from providing inaccurate results or errors resulting from unintended decoherence. There are different types of qubits used in quantum computing, with some better suited for different types of tasks. Here we have seen what is meant by qubits. Instead of 0 and 1, we have to store the information in the form of qubits. How do quantum computing works? As I said, there is a primary difference between classical and quantum computers. Is that quantum computers are use qubits instead of bits that store exponentially more information. Because quantum computing is very fast. How this very fast? It's stored in the form of bits. In the qubits. While quantum computing does use binary codes, qubit process information differently from classical computers. Here, what are the qubits and where do you come from? We'll see here. There are few more types of qubits in use as follows. The concepts is here: superconducting qubits, trapped ion qubits, quantum dots, photons, and neutral atoms. These are related from the physics. What is meant by superconducting qubits? We'll see here. Mode from superconducting materials operating at extremely low temperatures. These qubits are favored for their speed in performing computations and fine-tuned control. Then trapped ion qubits. This can also be used as qubits and are noted for long coherence time with high fidelity measurements. Quantum dots. These are the small semiconductors that capture single electron and use it as a qubit, offering promising potential for scalability. Means we can increase easily. The scalability is it should be functional. Even the number of particles are increased or dots are increased, it should be scalable, it should be compatible with existing semiconductor technology. Then photons. Photons are individual light particles used to send quantum information across long distance through fiber optic cables.
Video is not available, sir. Only that the points are there. Whatever you are telling definitions, it is not coming.
Can you see, madam, here?
No, sir. Only points are there. Most common types: superconducting qubits, trapped ion qubits. That is there. What is the meaning of that explanation? It is not there. It is in the next slides, or it got stuck, sir?
No. I'm explaining, madam.
Okay, sir. Thank you.
This is a brief definition from the physics.
Okay, sir.
Some terms are there: superconducting qubits, trapped
Okay.
on ion qubits, quantum dots, photons, and neutral atoms. Okay. Now we are looking the photons. What is the photon here? These are the individual light particles used to send quantum information across long distances through optical fiber cables, and are currently being used in the quantum communication and quantum cryptography. Then neutral atoms. This is commonly used in the neutral atoms charged with lasers, as well as suited for scaling and performing different operations. Okay, these are the some terms we are looking for the qubits. Now, as we have seen, there are the four principles of quantum computing: superposition, entanglement, decoherence, and interference. We'll see the superposition. What is the superposition? In the superposition, we can see this figure here. Superpositions here, a qubit itself isn't very useful, but it can be placed the quantum information it holds into state of superpositions, which represent the combination of all possible configuration of the qubits. Here we'll see that groups of qubits, maybe you understood that qubits, the group of qubits in superpositions can create complex, multidimensional, computational spaces. Complex problems can be represented in new ways in this space. This superposition of qubits gives quantum computers their inherent, allows the process for many inputs parallelly. Then another is entanglement. In entanglement, what is this entanglement? You can see here, entanglement means coordination or correlations. How the correlation is there? We can see this is defined as ability of qubits to correlate their state with other qubits. These systems are so strongly linked. There is a link between the two entities. When quantum processes or some processors measure single entangled qubits, they can immediately determine information about other qubits in the entangled systems. Here we can see the two entities are there. When quantum system is measured, the state collapse from the superposition of possibilities into binary state, which can be registered like a binary code, as we can see is a 0 or 1. Then a third principle is decoherence. Decoherence is the process in which systems in the quantum state collapse into non-quantum state. We can see we are looking the third principle here.
वो ड्राइव करता है पोस्टलर करूं क्या फोन
We are looking here the third principle, decoherence. This is a process in which system in the quantum state collapse into the non-quantum states. This can be intentionally triggered by measuring the quantum systems or by other environmental factors. These quantum computers to provide measurements and interact with the classical computer. Classical computers are the normal computers we are using the daily use, or the even supercomputers comes under the classical computers, but quantum computer. Fourth is the interference. Fourth principle is the interference in the quantum computing. We can see here, this is the environment of entangled qubits placed into state of collective superposition structures. There it looks like waves with amplitude associated with each outcomes. These amplitudes become the probabilities of the outcomes of measurement of the systems. These waves, you can see in the waves here in the figure, the waves can build on each other when many of them pick a particular outcome, or cancel each other when the peaks or troughs interact, amplifying a probability or cancelling out other both forms of interference. Now we are looking how the classical computers is different from quantum computing. As we have seen, classical computers store in the form of 0 and 1. Qubits, like we can say the example of coin. In the coin, there is a head and tail, or 0 or 1. But the coin is moving or tilt this way. It can see is a position. It can move at different positions. Here we can see that qubits follow the superposition principle and can exist as a 0 and 1 at the same time. The positions are going to change, and there are the different options in the quantum computing. But in the classical computing, we can see the information is stored in the 0 and 1. As we can see here, quantum computing is built on principle of quantum mechanisms. They are subatomic particles behave differently from micro level physics. These quantum mechanics provide fundamental laws. As we can see, our entire universe or subatomic levels, every system is a quantum system because it's looking. We can say this is a natural systems. For this reason, we can say that while conventional computers are also built on top of computing systems, they fail to take full advantage of quantum mechanical properties during their calculations. But quantum computers take better advantage of quantum mechanics to conduct calculations that your high performance computers cannot. Even supercomputers calculations is limited with respect to the time, but the quantum computing takes very less time as there is a hardware and the speed, and then it's increase the its processing time, and will give the results very soon. As I said, what is a classical computer? Classical computer, it's a beginning, we can say punch card adders to the modern supercomputers, traditionals on classical. These computers are essential function in the same way. These machines generally perform calculations sequentially, storing data by using binary bits, and each represent either 0 or 1. When combined into the binary code and manipulated by using logical operations, we can use computers to create everything from simple operating system to the most advanced supercomputing calculation. This is a brief about the classical computers. Then quantum computers, as we are discussed here, quantum computers function similar to classical computers, but instead of bits, quantum computers use the qubits. These qubits are the special systems that acts like subatomic particles made of atoms. Supercomputing electrical circuits or other systems data set of amplitude applied 0 or rather 1. But here in the quantum computings, we can see the states between the 0 and 1. This complicated quantum mechanics concept is called as superpositions. The process called quantum entanglement, those amplitude can apply to multiple qubits simultaneously. There it increase the speed to the quantum entanglement. If we are going to differentiate between quantum and classical computing, as we can see, classical computing is a very common multi-purpose. We are using daily use devices, store 0 1, processes data logically and sequentially. But in the quantum computing, we can see specialized and experimental mechanism. There is a quantum mechanics based quantum hardware that store information in qubits as 0 1 or superposition of 0 and 1 in between the 0 and 1 positions. The processes data with quantum logic at parallel. We can see there is a concept we are seeing the interference amplitude is going to modify or change. How the quantum computing is superior, how is going to solve the big problems in short span or less time. There are the lots of variables interacting in a computational ways. There may the great difficult tasks like sorting through the big database of modules. There are the different algorithms in the quantum because it's a superior as compared to the classical. It is a multidimensional computational space running calculations that behave like these molecules themselves. In engineering field, financial institutions, global shipping companies, or many more use cases are there that in this field they are going to solve the problems in their fields. In the use cases, The first factor theorized in the early 1980s. It was until 1994 that MIT mathematician Peter Shor published the first article related to the real-world applications on quantum machines. Then Shor algorithms for cryptography. Shor finding demonstrated viable applications for quantum systems with the dramatic implications, not just cyber security or this quantum computing having the different application in different fields like a cyber security or many more, in especially in medical fields is popular. We can see the use case in pharmaceuticals. Sorry. Quantum computers capable of simulating molecular behavior and biochemical reactions could massively speed up and research and development of life-saving new drugs and medical treatments. If we are looking this first use case in pharmaceuticals, if we are going to solve or we are going to see that in use case related to pharmaceuticals take the results, even supercomputers it takes more time, but in the the quantum computing it solve the problems in very less time because it is massively speed up, and the research in that life-saving new drugs and new medical treatments, new innovation in the medical field, though it is helping for this field pharmaceuticals for fast results. Second use case is the chemistry. We can see in that some reasons are quantum computers that impact medical research that might be provide undiscovered solutions for mitigating dangerous or destructive byproducts, because human beings cannot enter in that area, and we can use this quantum computing to solve the problems, especially in biological lab where human beings cannot enter. So the quantum computing is helping us to improve the catalysts that enable petrochemical alternatives to better processes for the carbon breakdown necessary for combating climate threatening emissions, or many more fields are there. Chemical reactions are there, so human being cannot enter, cannot observe. The quantum computing is helping us to solve the problems in the chemistry. In the machine learning, as we are interested in this field as a engineering field, this interest and investment in artificial intelligence and related fields like machine learning ramp ups, researchers are pushing AI models to new extremes, testing the limits of our existing hardware and demanding tremendous energy consumptions. This can also use, there are different algorithms, quantum algorithms related to the AI, look at the database, new databases, providing the speed up for the results to solve the machine learning problems nowadays. Quantum advantage versus quantum utility. What is mean by quantum utility? We'll see here. Quantum utility refers to any quantum computations that provides reliable, accurate solutions to problems that are beyond the reach of brute force to classical approximate methods. The problem-specific approximation methods carefully crafted to exploit the unique structure of the given problems. Quantum advantages. Broadly define the term quantum advantage refers to the hypothetical quantum computer capable of overperforming all classical supercomputer methods to some problems, even approximate methods. Quantum computers capable of achieving the quantum advantages for significant practical benefits. This is this calculating solutions in a way that cheaper, faster, or more accurate than available classical computers. This is the advantage in the quantum quantum computing. Quantum benchmark, we can see here. Now this is offers viable alternatives to classical approximation. As we have seen, there are many advantages of quantum computing. For certain problems, researchers say it will be useful tool for scientific explorations, that it has a utility. Quantum utility does not constitute a claim that quantum methods have achieved a proven speed up over all known classical methods. This is a basic difference between the quantum computing and quantum utility. Then layer fidelity. This is extremely valuable benchmark. This provides a way of encapsulate the entire quantum processor ability to run circuits while revealing information about individual qubits, gates, and crosstalk. By running the layer fidelity protocol, researchers can qualify the overall quantum devices, also gathering information about the individual components. If regarding the speed, if we are looking the speed of quantum computing, this speed matrix in the calculation is a CLOPS, that is circuit layer operations per second. It's a measured matrix. Currently, CLOPS is the measure of how quickly our processors can run quantum volume circuits in series. It takes the fast. It provides new way of benchmark systems that more meaningful to the people trying to improve and use of our hardwares. This matrix CLOPS makes it easier to compare systems to one another, to compare our systems to other architectures, and to reflect performance gains across the scales. As we can see, why this is scaling. Scaling means it's going to scale increase fast. How the scaling the quantum processors? As we know that qubits are stored in the qubits. Qubit processors use quantum computing have the potential to massively outperform bit-based processors. It can support the small number of potential qubits. If you are looking at example, IBM plans to introduce quantum systems 20 logical qubits capable of running 100 million quantums. It is expected up to 2029, and the goal of 2000 logical qubits capable of running 1 billion gates by 2033, because this quantum processor speed is increased scale. Especially Google developed the different labs are there, and whatever that problem solved by the quantum computing, it takes a very less time as compared to the supercomputing. Then we are looking for towards the hardware, scaling quantum hardware. This is a very powerful. Qubits are also quite error prone, requiring large cooling systems capable of creating temperatures lower than outer space. Researchers are currently developing ways to scale qubits, electronics, infrastructure, software to reduce the footprints and cost and energy usage. If we are looking the hardware, the quantum error corrections, as we have seen, this is our principle of quantum computing, decoherence. This is a process in which qubits fail to function properly and produce inaccurate results. This is a major hurdle for the any quantum systems or quantum computing. The quantum errors corrections requires we encode quantum information into more qubits than we would otherwise need. In 2024, IBM announced landmark new error correcting codes about 10 times more efficient than prior methods. And this can be solved that not solve the problems. This new code masks a clear path towards the running quantums. Now we'll see that quantum computers, how it will be useful as software and middleware. This quantum algorithm relies on highly performed and stable software stack to write, optimize, and execute quantum programs. If you are looking at software, there's open source and Python-based IBM used especially for that superconducting computers. There are different alternative technologies available for the quantum fields. There are different softwares are available which is compatible with the quantum computing. Quantum centric supercomputing. This will work with the modern and future classical supercomputing. In response, quantum researchers are preparing for a world where classical supercomputers can use quantum circuits to help to solve the different problems. There are the different components for the quantum computing. IBM quantum processors, we can see It's a composed of qubits laid out in various configured to allow communication. Quantum chips, also known as quantum data planes, act as the brain of quantum computers. As a core component in a quantum computer, quantum processors contains the system's physical qubits and the structure required to hold them in the place. There's a QPU, quantum processing unit. It's like a normal processing unit is a QPU. This include quantum chip, control electrons, and classical computer hardware required for the input and output. We can see here quantum computing components, the hardware and software. The hardwares are physical qubits, processor, control circuits, interface, detectors, chips for tapping ions, vacuum lasers, microwave or optical systems, wirings, refrigeration, housing like a package, signal shielding. These things comes under the hardware. In the software, we'll see here it's the main objective of your software is error corrections, control, processing languages, specifications, simulations, debugging, programming language, compilers, schedulers, optimizations, verification or validations, and function libraries. These things comes under the quantum computing softwares. Superconductors, as we know, your desktop computers likely use fan to get cold enough to work, but here quantum processors need to very cold temperatures, about hundreds of degree above absolute zero, because how to maintain the quantum computing components. We can minimize the noise and avoid decoherence to retain their quantum states. This ultra low temperatures is achieved with supercooled superfields. At this temperature, certain material exhibit an important quantum mechanisms. The electrons move through them without resistance. These effects make them superconductors. This is related to the hardware.
இதுலயே போறோம் பாப்பா ஏதோ சேஃப் டிரைவிங் மோடாமே இதெல்லாம் மாத்தி ஏன்னா
This we can see that temperature should be minimum here.
என்னனோ
The quantum computers use circuits with capacitors and Josephson junctions as a superconducting qubits. By firing microwave photons at these qubits, we can control their behavior and get to hold, change, read out individual units of quantum informations. This is related to the control. We have seen the superconductors control. Now quantum softwares. As we have seen, there are open source softwares also available. Researchers continue improving quantum hardware components, but that's only one half of the equations. The cruise of users' discovery of quantum advantages will be highly performable. Stable quantum softwares take to enable the next generation of computer algorithms. If you are looking here, the Qskit is an open source software development kit. We can short form SDK. Qskit SDK 1. The series is there. With over, we can see there are different universities and different colleges. They registered to this Qskit as an open source. They are using these softwares as a for the quantum software. There are the many applications of the quantum computing is used in the different fields. There are many applications we can see in the secure communications, optimizing industrial processes, complex chemical simulations. The first application we can see here, drug designing. Quantum computing overcome the limitations of existing computational methods. If you are looking the drug designing companies, existing companies, for any results, it takes so much time to calculations are there. But in the drug designing, that quantum computing helping us to employ entanglement and superposition to leverage and handle all the possible permutations of molecular behavior of drug efficiently. If you are looking the example here, pharma research outfits such as SRI International or AstraZeneca explore QC's means quantum computing's potential in modeling the proteins. This is one example. For drug designing, it will be applicable for the different drug designing or different like a virus are there for that for virus research. Then there are many permutation combinations for this any drugs related to that, any virus or any diseases. This permutation combination is possible through the quantum computing is very fast, which is not possible to the our existing supercomputing or supercomputers. Second application we are looking here, artificial intelligence and machine learning. In this we can see there, this is a potential to accelerate or improve the machine learning relative to classical performance. We can see here whatever the problems related to the artificial intelligence, this can be solved very fast. For example, IBM came up with promising machine learning classification algorithms that is possible through that quantum classical hybrid. Then optimization, third application is there in quantum computing can improve research and development, production processes, supply chain optimizations. This decreases manufacturing process related to the cost, also reduce cycle times. In the optimization, it can save our the time, it can save our the cost by optimizing elements such as path planning in complex processes. Next application in financial sector, quantum optimization for loan portfolios. If lenders can make better decisions, free up capitals, lower interest rate, and improve their offerings. Then next application is auto industries. QC's potential to simulate quantum mechanics could be equally transformative to other chemistry related. For especially auto industry want to harness the technology to build better car batteries. Now we can see that the issue of the car batteries are there. Last time we heard in the news the issue of the car batteries and that manufacturing stopped to introduce the new cars. The quantum computing is helping the auto industry to better car batteries. Cryptography related to the security. This is enable encryption, ensure hack-free data transmissions by using super dense coding, secure quantum communication protocols. Or we can see that is helping in the security field. Astronomy. This is one more application in that quantum computing could reveal the mystery of unique processes of universe such as Big Bang. It's very difficult to find out what happening in the universe or to find out what is in the universe and black holes due to its ability to simulate molecules and molecular processes of the universe. We can study very well with that quantum computing in the astronomy field. These are the many applications where the India stand for the quantum computing. There research is going on. As I said, that Google is invested so much amount at the international level in US. India is gearing up the accelerate indigenous efforts around the development of quantum computing. We can see the budget 2023 rupees 6,000 crore, USD 800 millions allocated towards national mission on quantum computing and technology spanning in 5 years. TCS National Qualifier Test 2023, they also taken initiative, TCS, conducted first of its kind online test to identify talent for building quantum computing skills and knowledge across Indian universities or different colleges. They are collected or they conducted the test to understand the quantum computing and find out the talent among the students or faculties. MIT initiatives. This is launched by Quantum Computing Applications Lab on AWS Cloud, focus on developing tools and methods to leverage quantum for critical national applications. Then next, quantum computing in India, we can see IIC, Indian Institute of Science. They established a dedicated quantum technologies and application center to conduct research around NISQ computing software and hybrid quantum classical algorithms. It is a research institute. They invest a lot in this quantum computing. Then Indian Institute of Technology, Madras, IIT Madras, undertaking fundamental R&D across quantum cryptography, communications, sensing, and networks, while also establishing Center for Quantum Information, Communication, and Computing. They are also working in this quantum computing field. This we are seeing as a quantum computing initiative in India. There are the different labs they